recorded for the benefit of those who are far off. So, we've wrapped talking about shafts. Which call next thing on the docket is looking at temporary attachment of members together. So, talking about fasteners, and we're talking about power screws. Power screws being kind of our way of getting two fasteners in a little more simplified way. When I say power screw, I mean something like this. If you are an old person or a nerd, this you might recognize this being like a DVD player, and that screw running across here. So that engages with this half nut here, that little plastic guy, and as the screw turns, it moves that nut back and forth. So this is how the player would traverse a DVD when it needed to, or the slide one, the slide that held the DVD when it needed to. And this is kind of where we're going to start. This being kind of the quintessential example of a power screw in action. So, in order to get there, we start here. So we're going to start at the very beginning, because it's a very good place to start. We're going to talk about definitions of various thread standards, as well as definition of different terminology when you come to screws. We'll get into mechanics, start talking about the stiffness of bolted joints, and how to play around with that, being preloaded joints. I want to get to fatigue, but we'll see how everything else goes. Cool. So, definitions. There's your screw. When you get a screw, there call I know some of this sounds simple, but just some things to make sure I'm on the same page. So threads on a screw are the actual, it's the actual helix that is engaged by a nut or other, whatever the mating part is for the screw. It's how it screws into things. That helix engages with a matched helix on another object. This particular example of a screw has a shank to it, or an unthreaded section. Not all screws have that. Also of note, this is a machine screw that you're seeing. If it was a wood screw, it would have a pointed tip to it. It does not. It's a blunt head. So this is a machine screw. Point B, no pun intended. So if you have a point on your screw, it ain't going to matter, because you're trying to push through aluminum or steel. It's not going to cut the same way it will in wood. So machine screws are blunt. It's called important things to note when you're getting a screw are the length. It's kind of a big deal. Note that this is always measured from underneath the head, so from the base of the head to the tip of the screw. The thing that determines the thickness of the head is, well, not to be weird, but the thickness of the head. So the head itself, the head type, determines how thick that head is. You can have low profile heads. You have pan heads, socket heads, hex heads, low profile versions of all of those. Really, the head thickness depends on how you want to drive it and what style of head you get. So that's why the length of the bolt is measured from underneath of the head. One thing to note, there is a small radius here where the head meets up with the body of the screw. We'll talk about that a little bit more later when we talk about the thickness of bolted members, because that radius is essentially a large part of why you use washers. It helps to decrease stress concentration. But we'll get there when we get there. So that's bolts. Any questions on that? Okay. But enough about that. The important thing is the thread itself. So when you talk about thread, we're usually talking about something that has, which usually will be thrown around major diameter, which if I take a bolt and slap a pair of calipers on it and measure from the top of the bolt to the bottom of the bolt, what I'm measuring is the major diameter of the bolt. So it's from the outside of the threads to the outside of the threads. That's the major diameter. If I measure from, if I take a really sharp-edged caliper and I dive in between the threads and go to say the and go into a valley, the top of a thread is a crest, in between threads is a valley. If I go from valley to valley, so like from there to there, that's the minor diameter. So it's the smallest diameter of the screw. As we've mentioned with gears before, there's also a pitch diameter. Essentially, it's the average of the two. The pitch diameter is the average of the major and minor diameters. It's taken to be where the threads contact with one another, or a nominal location for where torque is transferred for a lead screw. We'll talk about that a little bit more later on. This thread angle here will be important in a minute. It's 60 degrees for your typical UNC or ISO screws. Talk about that in a second. But the kind of last really important metric for a screw is this pitch. Pitch is how many threads you have in a given distance, at least depending on what thread specification that you are using. So the top one here is a unified thread specification. UNC is unified coarse. UNF is unified fine. You don't really have to worry about the whole difference too much. You just have to read the thread spec. So how this thread spec works, which is almost all English screws, is that it starts off with a thread number, which corresponds to a particular major diameter, dash the pitch measured in threads per inch. So that means that if I take this lead screw here, I can set it up on a ruler, and I can measure the physical number of threads that there are per inch. So that's me going to the ruler and counting, okay, there's this one thread going by to the ruler, 2, 3, 4, 5, 6, 7, 8, 9, 11, 12. In this case, this is a 3/8 12 screw. Weird, let's call you. You might go, wait a second. 3/8, it's not like a whole number. What the heck? Well, you are not wrong. So I put this up on Canvas, but I will pull it up here while you write down all the other stuff. Oh, unless I didn't see it myself. That's unfortunate. There we go. There we go. All right. So if I go on to a tap and drill chart, which is essentially a chart that gives you a listing of screw size, versus drill sizes and such are required to put that screw into place. It looks something like this for the English varieties of it. So I can look over here on the right, and I have my screw size. The smallest is 0, goes up through 10. Well, actually, the smallest isn't 0. You can get double zeros and triple zeros and stuff like that. Look at the major diameter, getting into pretty freaking tiny screws. So that's why you don't really see too many of them. But after you get past 10 or 12, it goes into fractional sizes. So when I say a 3/8 16 or 3/8 12 screw, I say the major diameter is 3/8. And then it has 16 threads per inch. Okay. You can also say this for like the one on the slide was a 632. So a number 6 screw has a major diameter of 0.138 because this is an English screw. So it's 0.138 inches, and then it has 32 threads per inch. All right. The chart also lists the minor diameter of the screw just for your reference, although that handily allows you to compute the pitch diameter because it's the average of the two. What this chart's really useful for, though, is building craft. So when I have a screw, I want to make a threaded joint. I'm going to pop back over to here for a second. Oh, stop. I want to make a threaded joint. Let's this over to here. I want to draw a picture. There we go. Just so you know, show Koi 6 that's what we're recording. So if I want to make a threaded joint, I'm going to have a screw. I believe this is a screw. It is a screw. All right. Look at that beautiful screw. Close enough. Forgot my work. Okay. So that's my screw. So if I want to put that in, so if I want to use that to secure two things together, I'm going to drill a hole through the first part. And then in the second part, I'm going to want to screw it in. I'm actually going to want to fasten it to that member so that they hit this guy, which is continuous. I just drew it as 2 separate pieces to illustrate the hole. Is clamped between the member I'm screwing into, or the nut that I'm screwing into, and the head of the bolt. Right. So all these things clamp together. As a result, because that's how I'm assembling this, I do not want the screw to thread into this first thing, this first piece of material, colored a little different, distinctly different, because I want that to be as firmly clamped as possible. If it's threading into that guy, as well as the guy below it, it's called how well everything's going to clamp is limited by how far the two materials are each moving relative to one another. It's going to be an absolute mess. Can you make a joint like that? Sure. So you got to get no. Oh, don't do it. Bad life choice. Because the strength of the screw comes from being able to clamp members together. So what you want is through that first hole, that first member, on something called a clearance hole. And if you're drilling a hole through a second member, you want what's called a tapped hole. You can also clamp things using a nut, but sometimes you actually have to put screws into material, right? So you need a clearance hole through the first one and a tapped hole through the second one. Question is, What size hole should they be? So the clearance hole should allow the material to slide freely over the bolt, right? Because you want that material to move around and be able to be without interfering with the second tapped member. Say what that means in a second. So when you want to figure out the size of your clearance hole, well, obviously it needs to be bigger than the major diameter of the screw, right? Because the screw has to drop through it. So how well it fits through it is essentially what kind of fit you want. Do you want it to be close? Do you want it to be free? We talked about those definitions a little bit when we talked about press fits. It's called, essentially it's just saying how much slop do you want, which can be nice for manufacturing, since you don't have to be as exact. Although it does mean that the hole can move around a little bit more. Right, so when we're building stuff, we always use a close fit. So like for a number 6 screw, a close fitting clearance drill would be a number 27 drill, because American drill numbers or drill sizes are weird. That is the actual number stamped onto the drill bit. Number 27 drill, which is 0.144 inches in diameter. So that's how you use this in order to get a clearance drill. A tap drill, so the idea is that I want to drill a hole smaller than the screw itself, so that I can myself physically cut threads for the screw to thread into. A tap being something that looks great, thank you. Okay. So a tap is one of those things on the bottom. You physically turn that into a piece of material and it cuts threads. So each one of those is a particular thread pitch and a particular diameter. Like you can get a 632 tap. It has the major diameter of a 632 screw and it has 32 threads per inch. You turn that into the material and it gradually cuts your threads. In order to use one of these, though, you need a hole that is a tap hole, or one that's drilled with a tap drill for your particular screw and thread size. It's screw and thread size because of the amount of stress you put on your tap when you're trying to cut threads. The more threads you're trying to cut, the greater force there'll be on the tap itself because of how they're made. So most of the taps you'll see around here are tapered. So start from not really anything. This is like the minor diameter of the screw. It gets steadily larger and larger and larger, which helps you to align your tap so it's parallel to the hole. There's more tap in the hole before it starts cutting. And then eventually you have a thread that's like way up. It's like way up here. So the fact that you don't the fact that you don't cut a full thread for that long, one, helps you align it in the hole more, and two is it's called what means you cut them a little bit slower. Like you start out cutting very, very shallow threads and then get thicker and thicker and thicker and thicker, which is kind of nice. It helps you not break things. This is always a good deal, especially when you're cutting 632s. They're supposed to be the weakest thread and diameter combination out of all the American screws. You get around this by using either a plug tap, which in terms of not having full threads until all the way back here, because as you might imagine, if you want to thread to the bottom of the hole, you can't do it with this tap. You get around it by using a plug tap or a bottoming or a finish tap. But all this said, that's why we care about the tap drill. So I can find that. I was jumping back over to my chart. Which I will eventually drag onto the screen. There we go. and can pick out the screw size, the thread count, and then on that same line for thread count, I come over and I find a drill size. So for a 632 screw, a number 6 screw with 32 threads per inch, I'd use a number 36 drill, or one that's 0.1065 inches in diameter. Cool, beans, we're all on board with that? All right. This works more or less the same way when we're talking about cutting external threads. So a tap, as you might imagine, the cutting things on the outside. So it's cutting in threads in a hole when you just drill with the tap drill. You can also cut threads on the outside of something, which is called a die. So if I come back over here, so this guy in the corner, that'd be an example of a die. So those flanges in the middle have the same teeth that are on the outside here. You put that on the outside of whatever shaft you want to cut threads on, the shaft being something that is the major diameter of whatever thread size that you're trying to cut, and you can cut your own threads. We have all the tools necessary to do that here. You can also do that on a lathe. It's just a little bit more tricky, but you can do it, but it's automated and faster and all that sort of stuff. Mass manufactured screws are usually rolled threads, not cut. They're usually a little bit stronger. You're cutting something, you're inducing cracks, right? But it's the way the threads were made for decades, if not more. So it's not exactly a bad way to do it. It works. Okay. Any questions on all that stuff? Oh yeah, about that. So thank you. I forgot where I got off of this. So ISO or metric screw users are you know that it's metric because there's a big M in the front, followed by the major diameter, the actual physical major diameter in millimeters. The thread pitch in metric is also listed as in millimeters per inch. Sorry, in millimeters per thread, not threads per distance. So that's an M3.5 screw has a major diameter of 3 millimeters. So that'd be one of these guys. So 3 millimeter diameter screw, and each thread is a 0.5 millimeter apart. In fact, this by 25 means that the whole thing's 25 millimeters long, which actually this one's 30 millimeters long. As opposed to an English definition where the 632 by 1 screw is 1 inch long. That's again from underneath the head to the end of the bolt. Cool beans. These are just 2 thread standards. Look at these guys. They don't look anything like it, right? Well, they look similar. I mean, they have threads, obviously, but what's the difference on those guys? Yeah. So those are pipe threads, or NPT threads. And this is where the definitions get a little screwy. UNC, UNF, ISO, they're big ones in the machining world, but there are a ton of thread specifications out there. NPT is National Pipe Thread. NPS is National Pipe Straight. BPT is British Pipe Thread, which ironically just didn't become American because of I think an American made a loom or something in the 1700s and decided to make their own thread standard, and it took over in the U.S. Anyhow, you have a crap ton of thread standards out there, and the trick for getting any of them to mate is based on the thread angle, the thread angle, the pitch of the threads, the diameter and whether or not it's tapered, and if so, how much is it tapered. So, so when you read these different standards, that's it's called or and when you want to mate parts together, it's kind of something you have to keep in the back of your mind. Now, can you figure out what is called what a thread is just by looking at it? Yes, because everything is defined in terms of diameter, pitch, length, and if there's a taper, the taper angle. So you can definitely figure it all out if you have a pair. If you have a pair of calipers and an example of whatever you're trying to find the measurements of. So that's like a super handy thing. The only exception to that rule is something I'm going to talk about in a minute. Am I going to bother waiting for that? No. Okay. So this guy need someone to find him the pitch on it. You're closest. So there you go. So that's a piece of 3/8 inch diameter screw. But it's what's called an Acme screw. Just and if you're thinking Wile E. Coyote, yes, it is that same kind of Acme. But things don't blow up, which is awfully nice. Now, what's kind of weird when you get into power screws, which we are about to get into, is that you have an addition. You have one more dial that you can turn when it comes to defining a screw. Which called thread number, which called measure diameter is still the same. Pitch is still the same, which for that guy is 13. Great, thank you. Let's just call it. It's
how exactly do you measure? Where's the first?
Yeah, so you pick one and you count from there. Your measurement will probably usually be like plus minus 1. So this is actually, I think, a 3/8 12. Yeah, pretty much. So this is a 3/8 12 screw. There are about, I think I found 3 different 3/8 12 screws because of how they shape their helix. So I can have a 3/8 12 screw. Wait for it. Don't do that. I can have a 3/8 12 screw. That has a helix that looks something like this. Yeah. And I could try, I have 12 of those per inch. Look at that beautiful screw thread. Woo. However, I can also have a 3/8 12 screw with a pitch like that. I can still have 12 threads per inch. So I'm counting 1, 2, 3, 4, etc. threads per inch because I mean I'm just angling the threads a bit more, right? I can still fit 12 on any given side of the screw in the same amount of space, right? My spacing is not very consistent, I'm sorry. But this is what's called a double thread screw, or a high speed screw. Because even though it's still 12 threads per inch, I'm covering more ground per rotation. So this is a high speed screw. And it's called 2-to-1 is fairly common. So instead of so if I have my regular 3/8 12 screw, it means I have 12 threads per inch. Or if I invert that, it's 1 inch per 12 threads, right? If I work out the math, one thread divided by, sorry, 1 inch divided by 12 threads, that means that I have 0.083 inches per thread. So if I turn my nut once, I'm advancing that nut by 1 thread, and I go forward 0.083 inches. If I have a double threaded screw, that means that I'm advancing 0.166 inches per rotation, or my helix angle has been increased such that the nut advances further per rotation. They usually go up by powers of 2. But I think I've seen a 4-threaded screw. So those are called. So that'd be a 1/3 of an inch per rotation. Okay. So you can get high speed screws. They're kind of interesting sub-breed. But usually you don't see those except for on power screws. A power screws being something that's used to move a load. So let's talk about that. So power screws. So one example of that is a lathe. If I can move this out of the way. So here's the lathe, just like the one that we have over in Sullivan, not Sullivan, library. So there's the length of the lathe. You have the spindle here where it holds some material that you're going to work on. You have your tool holder over here. This big crank moves this whole carriage, the big green thing here, or side to side. Smaller handle here, like this guy, moves the tool holder into and out of the page as you're presently seeing it. And this tiny guy here moves what's called the compound rest, which is the block that the tool holder is actually sitting on. So you can get really fine adjustments. If I take that apart a little bit, it looks like this. So each handle is connected to a screw, a lead screw or an Acme screw. We'll talk about the difference later. But that screw goes through a nut like this, which is rigidly, or as rigidly as possible, attached to the thing that you want to move. So in the case of this guy, which is the compound rest, that nut, that brass guy there, would be attached to the metal block that the tool holders resting on. So as I turn my crank, I'm moving that nut along, and because I'm moving that nut along, I'm moving the block with the tool holder forward. Makes sense? You can see the same thing on which called cargo aircraft. Actually, if you if you've ever flown in commercial and you've had a wing, had a wing seat, and the seat that's near the wing, usually a little behind it. You know those big oblong nacelle-like things that are spaced along the wing? Yeah, those actually hold lead screws for the aircraft's flaps. Like that's part of how those flaps extend. What you see is a fairing covering up the screw, because of how far down the flaps go, they need something to cover when you come around the land. So you got these things all over the place, because screws are really easy ways to make a rotating load from, say, like a motor, a linear translation and a linear force, without really occupying a ton of space. Like you don't need to make some intense telescoping rod. in order to get my compound rest to move. I just need to put a nut onto a screw that runs the length of however far I want the thing to run, right? So it's a really straightforward way to do that. And because a thread is a helix, essentially it's just a wedge. So it's a relatively efficient mechanism in order to do this. And by efficient, I mean a means of applying a longitudinal force from a rotary motion or from a sideways motion on the small scale. So that screws for you. But let's talk about how that happens if there are no questions on all that. Great. All right. So mechanics. So we'll be talking about square threads first. These are primarily used in what are called lead screws. So like the thing that we were just looking at, a lathe. That said, these is called square threads are not usually utilized because they're hard to cut. It's called Acme threads. So if you look at this little bar, nice catch. If you look at the profile of the teeth, I have to turn a little side on. You'll see that they're not square. They're just a little bit tapered. They're just a little bit tapered. In theory, it should be a 14.5 degree angle from the vertical there. So you look at the profile of an individual tooth, kind of like it's showing up on the thing. So when we're talking about, so when we're going through these notes on mechanics, we're going to talk first about square threads. Then we're going to talk about Acme threads, or Acme, if you want to pronounce it that way, and then we'll taper things from there. One other note about Acme threads: square threads really are preferred in terms of transmitting loads. This being because Acme thread, it's angled a bit, so you have a bit of a wedge. So you guys remember when we played with the Lathe center? The only thing holding the tool in the Lathe center was a wedge. If I just kind of let it sit there, I can pull back out easy. As soon as I gave it the least tap, as soon as I pushed those two wedges together, you couldn't pull them apart anymore. Not without tools. As you might imagine, that's not a desirable quality of a screw. You want to be able to turn those screws, right? So as soon as you start to taper them, you'll increase the amount of friction between the bolt and the thing that's mated into. If I'm putting the fastener into something, say I'm putting a screw into a hunk of wood, I want friction. And that's why screw threads have a very aggressive pitch, a very aggressive thread angle. It's called usually 60-degree thread angle. But if I have a lead screw, if I have something that I want my nut to move around on, so I'm trying to drive it from one position to another, then I don't want friction. That's like a bad thing. So Acme screws, a little bit more friction, a lot less expensive. That's kind of the trade, and that's kind of the trade-off with a lot of these things. But regardless, we're going to start by talking about square threads. So our free body diagram for the day. So we're talking about some square threaded screw. There's some lead angle, lambda. That's that guy there. That describes that can be related to the thread pitch. Because if I have so many threads per inch, that means I need such and such a lead angle in order to accomplish that. So that lead angle also is directly the kind of, if I take a slice out of this screw and look at it from just one side, that'd be like these wedges here. That lead angle is kind of the slope of my wedge. It's the slope of my thread. So you might imagine the top surface of this wedge being the top surface of my thread here. The point of this wedge is just the starting point of the thread down here. I just draw a line across and up, and that's the rest of this wedge. All right, does that make sense? Cool. All right, and that lead angle lambda is the inclination of this thread. If I know the major diameter and I know how many inches per thread, I can figure out what that lead angle is. As you might imagine, well, we'll get there in a minute. Okay, cool. So we got all that. If this is a lead screw, we're turning it, right? And we're creating some force because we're moving a nut on it. So we have some nut here that's called that we're threaded into. Most nuts are round or they're even in some way, and the bolt goes through the center so we don't torque it. So we can assume that the load is evenly distributed on each side of the nut. And by doing this third law, that also means that we have a thrust force on the screw itself. So when I'm thinking about how to put this screw in, sure, I'm going to need a couple of, sure, I'm going to need like a bearing for the screw to ride on or for my handle to ride on. But I'm also going to need something to take up that thrust load too. Could be a thrust washer, essentially just a nicely oiled washer sitting between the rest of your her material and which calls some shoulder on the screw or some collar on the screw, something that doesn't move and the screw is just riding with. You could also use a thrust bearing or something like that. You have to eat up that thrust load somewhere. It's not only pushing on the thing going to move, it's also pushing on the quote unquote fixed object as well. All right. So if I do a free body diagram with that then, so I have, how am I going to say this? I have whatever the axial load is pushing into my face. Say that I have a load and I'm trying to raise it. Let's start with that. So I have some load on this nut. I'm trying to raise that load. So naturally there's going to be some force pulling down on my screw, right? That's that force F. However, I'm also going to have some load from me trying to raise it, right? So in A, I'm turning the screw from right to left, moving that wedge from right to left, so that I move that, so it's just that I'm moving my nut upwards, right? And as a result, I'm applying some torque. That torque is acting at some mean radius or some mean diameter, dm. You're saying that that's our pitch diameter before, or the diameter at which we consider for loads to be transferred for a screw. So whatever torque I'm using to turn it, and torque is force times radius, blah blah blah. I can get the load that I'm applying, the force that I'm applying in order to move that load upwards. However, I have two materials in contact with each other, so I have some amount of friction also, and all that I also have to overcome. And that friction comes as a result of some normal force, which of course is just a reaction to the applied load. Okay, any questions on that? Cool. We go to actually finish this, or I just end up stopping in the middle. Dang, I'm probably going to end up stopping in the middle because I have to explain that. Okay, well, we're going to pause there then. And on Wednesday, we'll pick up with power screw mechanics and start writing out some equations for how much force and torque is required to move these loads around and go. Cool. All right. Thanks for stopping by.